So our work with our equations has shown that it doesn't matter what combination of acid and base we use, that it boils down to being the same reaction, that a hydrogen ion from the acid meets and joins with a hydroxide ion from the base to form a water molecule. Now we know that's an exothermic reaction. The reaction produces heat, and the inference is that it doesn't matter what combination of acid and base we use, we should end up with the same heat of neutralisation. And I'm wanting to go through the calculation to remind you how to do that. So in the prac work, you're going to get a polystyrene cup, and in that cup you're going to put your acid and base combination. I'll just choose hydrochloric acid and sodium hydroxide. That's one combination that can be used. To remove one variable, you're going to get a 1 molar solution of both. And we're going to put in equal amounts. So let's just say, for the sake of the calculation, we're adding 50 mils of each. So the aim would be to get the temperature of one of the solutions, which is your beginning temperature, add in the 50 mils of the other solution, stir with your thermometer and record the highest temperature change. And that's the one that's relevant in our equation. So we know using the MC delta T calculation requires 3 steps. And our first step is that the heat released is equal to the mass of the water heated times the temperature change, MC, the specific heat of water, times the temperature change of the water. Now here, the mass of the water, we're just assuming that the solutions aren't there, so we're just taking the total volume of here. So it would be 100 mils or 100 grams, it's the same because the density of water is 1, times the specific heat of water, 4.18, times the temperature change. So we'll just say that the temperature change was 5 degrees Celsius, times 5. Now if we get an answer for that step, our answer will be joules at this stage. And I get 2090 joules, and we know that we're wanting an answer finally in kilojoules per mole. So on our quest for that, we're going to divide by 1,000, and at this step we've got an answer of 2.090 kilojoules. Now our next step is to find the number of moles we're talking about, and on first glance you think, oh, well I've got 2 solutions, so what are we talking about? But we've set it up that it's going to be the same whether we do it per mole of the acid or per mole of the base, because we've got the same concentration and the same volume each time. So we're going to get the moles, I was going to say moles of the acid, but I could also say base because the answer is going to be the same. So here the relevant equation would be concentration times volume. We've set it up with easy numbers, concentration of 1, the volume of 50, but remember to convert it into litres. So we've got 0.05 of a mole, so we're almost there. Our heat of neutralisation, the heat evolved when acids and bases react and form salty water, would be our, so the heat of neutralisation. We're going to take our answer in 1, 2.090 kilojoules, divide by our answer in 2, and we'll have our answer in kilojoules per mole. So I've got the answer from here, I need to convert into kilojoules, and then divide by our number of moles. And I get 41.8 kilojoules per mole. And then we're going to add a minus sign there because our temperature rose. It's an exothermic reaction. So we're hoping that when the class does this practical with different combinations of acids and bases, that we all end up with the same value because that's what the theory is leading us to believe. Thank you for watching.